Now it's on. All right, hello everybody, and welcome to the College of Arts and Sciences Speaker Series. Today we have Dr. Larry Nittler with us. He is a cosmochemist studying the origin and evolution of the stars, the galaxy, and the solar system through both laboratory analysis of extraterrestrial materials, like meteorites and returned comet and asteroid samples, or by planetary or remote sensing via spacecraft. Dr. Nittler has played leading roles in the analysis of comet and solar wind samples returned by NASA's Stardust and Genesis missions, respectively, and has served as deputy principal investigator on NASA's Messenger mission to Mercury. He is currently a NASA participating scientist on the Japanese asteroid sample return mission, Hayabusa 2, and a member of the ESA/JAXA Repi-Colombo Mercury mission team. Dr. Nittler has received the Alfred O. Neer Prize of the Meteorological Society in 2001 and was named a Fellow of the same society in 2010. Asteroid 5992 Nittler was named in his honor. And without any further ado, Dr. Nittler.
Thank you. Thank you very much. I very much appreciate the invitation to come up here and visit. It's a lovely campus and a lovely drive up from Phoenix. And I don't get to give talks in domes very often, so this will be fun. So yes, I'm going to talk about a very wide-ranging thing here, but one of my very, very favorite subjects, one of my great scientific loves, which is something called presolar grains in meteorites. And I'm going to do this in the form of a couple stories, but I probably have a little background here first. So. For those of you who may or may not know the whole history of the solar system, about 4.5 billion years ago, the solar system looked like it did sort of on the left. That's an artist's rendition of a protoplanetary disk, which is an accretion disk of gas and dust forming the sun at the middle. The bottom picture is a famous picture from the ALMA telescope of such a disk forming today, a new star and planets today. And the basic idea here is that you have dust growing into rocks, growing into planetesimals, growing into planets. And one important point here is that we have small bodies in the solar system, asteroids, comets, that are surviving planetary building blocks. They never got incorporated into planets, so they provide a record of what was there at the very beginning. And we get samples of these because sometimes bits of asteroids smash into each other, knock rocks off, they fall into the gravity well of the sun, and if we're lucky or unlucky, depending on the size of the rock, it intersects the Earth on its way into the sun, gets to the ground, and we call it a meteorite, and then we can study it. We're also can collect cometary dust by aircraft in the atmosphere, and we're increasingly having missions that go out to these bodies, pick up material, and bring it back to Earth. So basically, these primitive extraterrestrial samples, I'm talking about primitive ones, are the ones that have not seen any melting, so they really are a good record of what was originally in the protoplanetary disk. There's a picture of a meteorite sitting on the desert, shiny black crust from melting in the outer surface, melting in the atmosphere. We get dust from comets. This is asteroid Ryugu. I will be talking more about that. For those of you who have maybe not seen a meteorite, I brought one, can pass it around. I guess I'll start at the back. So this rock is the oldest thing you'll ever touch. You can pass it on. And that's called a chondrite, and that is a little chunk of an asteroid that fell in Africa at some point and was picked up on the Sahara Desert, picked up and collected. So anyway, I consider these samples fossils. They're non-biological fossils, but they contain this record of the starting materials of the solar system, the physical and chemical processes happening during planet formation. We can use radioactive isotopes in these meteorites to determine the timing of processes in the early solar system. And the good thing is we have them in the lab. We have ever-increasing ability to study things in the lab at smaller and smaller scales with more and more precision. So compared to, say, trying to interpret data from spectra, well, there's always, never mind, I won't start comparing because there's always advances in technology in every field. But the point is that this is a way of doing astronomy and astrophysics in basically a geochemistry or a material science lab. And I'm going to focus here on the starting materials of the solar system. And because they can provide us some information into what I call the cosmic recycling process. And you can look at this diagram, this cartoon, and basically material gets cycled in and out of stars through the whole history of the galaxy. So stars are formed from molecular clouds that have gas and dust. They form this protoplanetary disk. The evolution of the star depends on the mass of the star. We'll talk a little bit about that. But a low-mass star like the sun becomes a red giant, becomes a planetary nebula, and spits a whole lot of new dust and material out into space. Similarly, a massive star explodes as a supernova, synthesizes all kinds of heavy elements in its core, and puts that out into space. It forms the next generation of clouds, the next generation of stars. So this whole process goes on and on and on. We're now at 14 billion years into the Milky Way or so. And the solar system formed 4.5 billion years ago from material that had been through a few of these cycles. So if we can study the starting materials of the solar system, we can tell, it can tell us things about this whole process, or at least we hope. So I'm going to do this in the form, I missed, it's a brand new computer and I forgot to transfer the font. So this was a cool Star Wars font. Anyway, not anymore. I'm going to do this in a couple of chronicles, a couple of stories. I'm going to tell a couple of stories to give the history of a couple of microscopic dust grains found in meteorites and the story they tell. But our story starts about 6 billion years ago when a little portion of a molecular cloud, so for example, this is the very famous Hubble image, unless this is the Webb image, I'm not sure which one now. I think this is the Webb version of the pillars of creation in the Eagle Nebula, which is a star-forming region, and you can see little blobs of gas, which is where new stars are going to form. Collapsed into, so about 6 years ago, maybe a 2 solar mass clump of gas and dust collapsed into a protostar and then became a star. And this star essentially spent the next little over 1 billion years trying not to collapse under its own weight. So the reasons stars are shining, like the sun, is that they have a lot of mass, gravity's trying to push that mass down, and the star doesn't want to collapse, so it's pushing back by creating heat in its core to heat the gas to provide gas pressure, PV equals nRT, and to fight back against gravity. Now, the way it's doing this is by squeezing the hydrogen in the core so close together that it can overcome the electrostatic repulsion and undergo nuclear fusion. And the reason this releases energy is that a helium nucleus weighs slightly less than 4 protons. So if you can combine 4 protons into a helium nucleus, you release a little bit of energy, the E equals mc squared. That little bit of energy is about 27 million electron volts. Now, not everyone, I mean, this is a physics department mostly, so I think people have some idea of energy, but we think about energy in a lot of different ways in our lives. So I decided to compare it to the most direct energy unit we usually think of, which is the energy we get from eating food. And each M&M is about 3 calories, which is actually 3 kilocalories. When you convert that, it turns out that every one of these reactions in the sun's core or in our star's core releases the equivalent of about 10 to the minus 15 M&Ms. So tiny bit of energy compared to what we get from chemical energy eating food. So wow, how does that keep a star going? Well, because there is so much hydrogen burning all the time. When you look at the luminosity, our star is actually burning about 30 moles of M&Ms per minute in terms of the equivalent energy. So that keeps the star burning, shining brightly for 1 billion years. And I will just mention, so there are multiple ways you can turn 4 hydrogens into a helium nucleus in a star. The most common way in the sun, what's happening is through something called pp chains, where you have 2 protons forming a beryllium or a deuteron, and then the deuteron's building up into, sorry, I shouldn't have said beryllium. Deuteron's a set of chain reactions to make a helium and releasing this energy in the form of gamma rays. There's also, in more massive stars, it's happening a little bit in the sun, but slightly more massive stars, it becomes important, is if you have any carbon, nitrogen, and oxygen around, there's a set of catalytic nuclear reactions, you can kind of see it here, that basically are rearranging the isotopes of these elements, but what they're really doing is taking 4 protons and turning them into an alpha particle. So hydrogen burning, releasing energy, pushing back against collapse of the star. A side effect of this is the production of carbon-13, nitrogen-14, and oxygen-17. This is, in fact, the source of the nitrogen we're breathing in this room. Or we're breathing it, we're not using it, but of course, most of the molecules in this room are nitrogen-14, and they're produced by this side effect of hydrogen burning. So a lot of the periodic table, a lot of the elements that we depend on for life and everything are essentially side products of the process of a star trying not to collapse under its own weight. Anyway, so about after it ran out of hydrogen in its core, our little star basically the core starts collapsing because it's no longer can fight against gravity. It heats up. That heats up the envelope and makes it expand and become cooler and redder, and we call it a red giant. This will happen to our star in another 4 or 5 billion years. This is a more massive star, so it happens faster. But when it becomes a red giant, when our star became a red giant, there were convection processes that mixed some of the ashes of that burning from deep, 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 deep in the star into the envelope of the star. And at that point, it included this material that had experienced this CNO cycle burning. And so in this case, what I've plotted here is the relative abundances of the 3 stable oxygen isotopes. Most oxygen is O16, but there's a little 18 and 17. If the star started right here, after this process, the surface of the star is now jumped up, has a whole bunch more oxygen 17 than it started with because of the CNO cycle. So at this point, the star no longer has the same composition at the surface that it did when it formed. So let's keep going in time. The core eventually gets hotter and hotter till it reaches about 100 million Kelvin, which is not cool. And that actually ignites helium burning. So helium, three helium nuclei combine to form carbon. Some of those will continue to capture an alpha particle and become O16. So the core turned into a mixture of carbon and oxygen. And this takes a few tens of million years to burn all the helium, at which point the star expanded again, and we call it an asymptotic giant branch star. And that's because on the Hertzsprung-Russell diagram, which plots luminosity versus temperature, it again looks, it's close in the same part of the region to where the red giant stars are. So it's asymptotic to the red giant. Astronomical nomenclature can be all over the place, but it's reasonable. So we call it, when I say AGB star, I'm talking about a star that has already undergone both hydrogen burning and helium burning and has expanded into a red giant. These stars are super interesting. They have this core of carbon and oxygen. Then they have these little shells of hydrogen and helium that are continuing to burn nuclear fuel. So there's still some fusion going on, producing energy. And then there's a massive convective envelope. And so what's going on here is, and then at the, and it's this very convective envelope. It gets far enough from the heat source that the temperature of that starts to get cool enough that some of the atoms can condense into dust grains. These dust particles then get hit by radiation pressure from the star, pushes on them, and that also pushes the gas, and it drives a very strong wind that pulls the material off the star into space. Here's an ALMA view of an AGB star, and you can see it has all these shells, because this is a pulsating thing where it shoots out some material, comes back, shoots out more material. What's next? So the important thing here, I just said all this, we have the strong wind, so we won't worry about that. Of interest to us for the Stardust story is that while it's on this phase, in the hydrogen burning shell, hydrogen burning is affecting magnesium isotopes and making an isotope called aluminum-26, which is an unstable radioactive isotope of aluminum. We don't think about it in daily life because the half-life is only 700,000 years. So even if the Earth had formed with any aluminum-26, it's been gone for most of the history of the planet. So we don't really think about it. But it's being made in this star and mixed into the envelope during this what we call dredge up. And for our story, what I'm going to say is at about 1600 Kelvin, very far out in this atmosphere, a little crystal of aluminum oxide, like a little sapphire. Sapphire is a gem of aluminum oxide. Condensed, the aluminum and oxygen atoms came together out of the gas phase and formed this little tiny crystal couple hundred nanometers across, very, very small dust particle, and the stellar wind drove it into space. And this grain is enriched in oxygen-17 and aluminum-26 because those isotopes were brought into the atmosphere, which is going to be very important. So here's when the AGB star is at the very end of its life. It spits off its envelope, it gets the gas and dust light up. It's called a planetary nebula, some of the most beautiful things you see in the sky. This is a beautiful James Webb picture of a Southern Ring Nebula. And we got this wind blowing, and so this little grain got blown out into interstellar space. It spent some time in the interstellar medium, maybe hundreds of millions of years, and eventually became trapped in a molecular cloud, a star-forming region. Not this one, this is one we're imaging today, and the one we're talking about was billions of years ago, but something like that. This molecular cloud, part of it condensed to form a new star. And that star became our sun. And so we have this protoplanetary disk, and somewhere far out from the middle of the forming protostar, in the outer part of the disk, you have this accretion process I mentioned. We have mixes of dust and ice particles condensed together to grow into bigger objects, pebbles and rocks, and eventually into an asteroid-sized object. Now I'm going to get into even more interesting physics. We now think that very early in the solar system there were dynamic instabilities, that we had the giant planets, we had these forming giant planets. We might have had 5 giant planets early on, not just Saturn, Jupiter, Uranus, and Neptune, but a 5th one. These things were interacting with each other gravitationally, and went unstable. This is called the Nice model. And we think this happened because it explains all kinds of weird features of the solar system, how the asteroid and comet orbits are inclined to the disk, the structure of the Kuiper belt, which is where the comets come from out in the outer solar system, structure of the asteroid belt. It ejected a whole lot of materials, mixed small materials from, like small bodies from the outer solar system into the inner solar system, including, say, an icy asteroid containing our little sapphire grain got moved into the asteroid belt. And at some point, collisions in the asteroid belt disrupted our planetesimal, our big asteroid, into smaller asteroid, broke it into a bunch of pieces, which gravitationally reassembled into basically a rubble pile shaped like a diamond. This is a photograph taken by the Hayabusa 2 spacecraft of this asteroid called Ryugu, and moved it into an orbit that crosses Earth's orbit. From out between Mars and Jupiter, came much closer to the Earth. Hayabusa 2, I should have updated that picture. Anyway, so Hayabusa 2, the Japanese Space Agency decided they wanted to go get material from an asteroid and bring it back to Earth to study in the lab. And this was a mission that was launched in 2014. In 2018, it rendezvoused with the asteroid Ryugu and took all kinds of data with various spectrometers and images to understand the asteroid. And it also touched down twice on the surface and scooped up some material to bring it back to Earth. And it was returned in late 2020. It is currently on an extended mission, even though the spacecraft dropped the capsule containing the sample to the Earth. The spacecraft kept going, and it's actually going to visit 2 more asteroids, the first one this summer, and take some pictures and some data. Anyway, it was very exciting. In December of 2020, the spacecraft dropped this capsule that made this fireball across the sky like a meteorite, but that is actually this capsule. Landed in the desert in Australia, and you can see the parachute here and the little thing. Here's a guy who had just picked up the sample return capsule to carry it back. They brought it back to Tokyo to a lab where they opened it up in this very fancy vacuum system where they could open it up completely under vacuum. And they discovered they had brought back 5.4 grams of Ryugu. That doesn't sound like very much asteroid material. 5 grams is not very much material. But with modern microanalytical techniques, it's an enormous amount. We answered basically all the top-level science questions of the mission with 100 milligrams of this sample. And so it's really amazing to have stuff like this just brought back from space. And I was really lucky to be part of it. So here's a picture of the actual sample collection. What it's doing is shooting a pellet into the regolith, and then that knocks material up into a canister. See if you can tell when it hits. So lots of material going up. And it was in that time that a few grams of material went up into the little canister. There was a Japanese scientist with a couple students who analyzed every single one of these fragments in this movie for its size and shape and to reconstruct something about the properties of the surface. An enormously difficult job. Had a nice paper out of that. And I love seeing the shadows of spacecraft on planetary surfaces. There's the little shadow of the spacecraft and its solar panels. Anyway, so it was very, very exciting. And I was part of this team, so I got to use this, got some of the sample to measure, and that's a picture of me in front of an instrument called the NanoSIMS, which is nanoscale secondary ion mass spectrometer. This is a postdoc I was working with named Jens Barasch, who's now in Scotland. That's me. This was at my lab at the Carnegie Institution in Washington, D.C. before I moved to Arizona, where I have a similar instrument. The basic idea here is that this is a laboratory technique. It's very, very most used in the semiconductor industry for quality control, looking at the silicon wafers and so on. But it's very, very useful in geochemistry, cosmochemistry, because you can use a beam of ions. You basically focus a beam of, say, cesium ions into a very small beam, say 100 nanometers across, and you smash it into a solid sample. And it's like sandblasting the surface. These ions knock atoms off the surface of the sample. Some of those atoms can be ionized in the process, and once you have an ion, you can steer it with electric fields and magnetic fields. And that's what we do. We put it through a magnetic sector mass spectrometer and then measure what the composition of the atoms are. So this allows us to measure the isotopic and elemental composition of solids on very, very small scales. And we did this. And this is what we found in one of our Ryugu samples. What we're looking at here is a 10 micron by 10 micron, oh no, it's more like 5 microns, I guess, region of a piece of a sample of this asteroid brought back from space. And what we've done is measure the oxygen isotopes and then constructed this image, which is the ratio of oxygen 17 to oxygen 16. And this is, the color scale is relative to solar. So solar would be at 1. So basically the ratio of everything in this room would be looking like this color purpley thing. And we see this one little spot that has, that is very, very enriched in oxygen 17. And it essentially sits here on this plot. Remember, this is our little sapphire grain. And we call this a presolar grain because this isotope anomaly proves it existed before the formation of the solar system. But we can also tie it directly to the astrophysics and say this came from a 2 solar mass star that had undergone this dredge up of CNO cycle hydrogen burning products. So that's very cool. I mentioned aluminum-26. I also mentioned that aluminum-26 only has a half-life of 720,000 years. So obviously, we can't measure aluminum-26 in this grain that we say formed 7 billion years ago or whatever, or 5 billion years ago. But what we can do is measure its decay product, magnesium-26. So aluminum-26 decays by beta decay to magnesium-26. When it does this, it releases a gamma ray. And so there's also gamma ray astronomers have constructed maps. You can detect it, the gamma ray from this. So we know that aluminum-26 is distributed throughout the galaxy, being ejected by supernovae going off. So it's associated with the galactic disk and with star forming regions. So it's a really important isotope for astrophysics. It's a really important isotope for the early solar system because we can use it as a radioactive clock. And it's really important for us here in presolar grains because we can detect it and tell that it was in the star. And how do we tell that? Well, if we look at the sun, this is the relative abundances of the 3 magnesium stable isotopes and aluminum. But we look at our little aluminum oxide grain, there's very, very little magnesium in the crystal itself when it formed. It was basically almost pure aluminum oxide. So when we measured the composition of it, we see a lot of magnesium-26 and almost no magnesium-24, 25. So that's a clear sign of radioactive decay, that this magnesium was once aluminum, and we can calculate that it was about 1 in 1,000 with amount of aluminum-26 to 27, and we can compare that with what's expected for AGB stars and learn more about the nuclear processes happening in that parent star. So that was a little cartoon to tell us how we get to how we know we have presolar grains and the history of a single grain. Now we have tens of thousands of these now, and each one has its own story to tell. I won't tell you all 10,000 stories. But essentially, this is another cartoon like I showed before. Essentially, these are fossilized pieces of ancient stellar matter. The atoms condensed together in a stellar environment, and nothing has happened, or very little has happened to them in the intervening billions of years, to the point that we can extract these and measure them today. So it's like having a chunk of stellar material we can study in the laboratory. They're very rare. They're on the order of tens to hundreds of parts per million of these meteorites. So it takes a lot of work to find them. We've spent decades developing automated methods and chemical methods to concentrate them and so on. But we know how to do that. And the isotopes are absolutely key. And the reason is that when the protoplanetary disk formed, it was very hot, and even in the molecular cloud before, a lot of the material that existed before got homogenized. And in the disk, most of the pre-existing dust got evaporated and recondensed, and everything got isotopically homogenized. And that means that the isotopic composition of the sun, the Earth, Jupiter, comets are all pretty similar. There are very, very important differences that tell us a lot about the formation of the planets and the sun, but they're much smaller variations. They're more on the order of percent variations compared to, well, I'll show you in a second, due to, there's all kinds of physical and chemical processes that can cause percent level or less than percent level changes in isotopic composition. These are used in ecology and biology and all kinds of things. So when we eat food and take the carbon from the food we eat, when that carbon gets incorporated into our cells, it's about 2 parts per thousand more carbon-13 left behind in our cells than was in that food. But that's 2 parts per thousand. When we look at the presolar grains, as I showed you a second ago, do I have the slide? I guess I don't have the slide I'm going to say. But the variations can be plotted on logarithmic scales. So I showed you that the sapphire grain was 5 times higher at O17 to 16. The whole range of oxygen 17 to 16 for material formed in the solar system is maybe plus or minus 5%. So if you go to a factor of 5, we have grains that are a factor of 30 times higher than the sun. It's pointing to nuclear reactions. That's the only thing in nature that can make such large variations, and where nuclear reactions happen is in stars. So that's how we know we have stellar material that we can study. And because very little has happened to them since they formed, they've been used as extremely useful probes of a whole wide range of astrophysical and cosmochemical processes. A lot of it's about how nucleosynthesis occurs in stars. What nuclear reactions are happening, how are the elements synthesized, and that's related to how stars evolve and all the processes going on there, and mixing processes in different parts of stars, the evolution of the galaxy. Because these are physical dust particles, they also give us clues to how dust forms in space, tells us clues to what dust is in the interstellar medium and how it's processed in the interstellar medium. Dust is incredibly ubiquitous in the universe. It's both astronomers view it as both, I think most astronomers view it as annoying because it blocks starlight and changes, absorbs it and re-emits it at different wavelengths and so on. So it complicates observations of non-dust, but it's a very, very important part of the evolution of the galaxy. So it's important in its own right, and we have actual grains that we know absolutely were in interstellar space for part of their lives. So they're very, very important. These are some electron microscope pictures of a bunch of these. They range from nanometer-sized diamonds, which are a little ambiguous in their origin because they're so small, to oxides, rubies, and sapphires, and silicates like amorphous silicate glass and olivine, and we have things like silicon carbide and graphite. And when you take these graphite grains, you can slice them with a diamond knife and look at them in a transmission microscope and find out some of them have subgrains of other materials. So this is a grain where you have a titanium carbide grain that condensed in the star, and then graphite accreted onto it to form this kind of this sphere of carbon. So all kinds of interesting things. And we use these different tools to study them. So I already mentioned nanosims, which allows us to measure various isotope ratios. There's a couple of labs, 2 labs to be precise, one in Chicago and one at Lawrence Livermore National Lab in California, that use lasers to blast away material from a grain and then selectively ionize an element you're interested in and measure it with a mass spectrometer. When you do this, you can measure like the isotope composition of heavy elements that are very, very rare. So you're measuring the strontium composition of a micron-sized silicon carbide grain. It's just kind of mind-boggling that it's even technically feasible. But when you do these measurements, they provide important information about how stars work. And so I already mentioned we have oxygen-rich stardust. So our little sapphire grain that I told the story of sits right here. But all these green and red symbols are grains we found. And like I mentioned before, they span orders of magnitude in their oxygen isotopes, whereas the whole solar system sits just down in a little thing. We can compare them, in this case, to observations of some oxygen-rich red giants. You can measure their composition with spectra. And we see that most of the grains actually overlap the stars. So this is strong evidence that these grains come from this type of star. Not these grains, because they don't match. We have to use modeling to figure out where they come from. But in terms of AGB stars, we figured out that most of the grains are from AGB stars. And you can, I don't want to go into details, and this is a fairly old paper at this point, but the point is these symbols are grains, little grains of oxide grains we measured in a meteorite. And these other symbols are theoretical models with different parameters. And we can obviously use the grains then to test these models. And if the models don't match, go back to the people who are doing the modeling and say, hey, this doesn't match. Can you figure out why? And this has been done for a lot of elements in a lot of different grains. And in some cases, it's been found that the models were fine, but the nuclear physics input they were using for the models was wrong, that the reaction rates were incorrect. And people have gone and remeasured nuclear reaction rates and found, oh, yeah, that was wrong. So this is a case where looking at these grains from a meteorite indicated the need to do a very complicated nuclear physics experiment, but improved our understanding of nuclear physics. I also mentioned silicon carbide. Silicon carbide is the best studied grain, even though it's not the most abundant. They're also from these AGB stars. And again, we can look at these isotopes, whereas everything in the solar system sits basically right around this red vertical line here. These grains span orders of magnitude in their amount of carbon-12 versus carbon-13. And when you compare them to these carbon-rich AGB stars, there's an almost perfect match in the distribution. So we think these grains come from AGB stars. And going back to this cartoon, the idea is that you're making a lot of carbon here in this region here from the helium burning shells making carbon. That gets mixed into the envelope, and eventually the star becomes carbon rich and that has more carbon than oxygen. And that's when you start making things like graphite and silicon carbide that we find in these meteorites. You also see silicon carbide in AGB stars directly from the infrared spectra, that there's a feature at 11 microns. So this is where these little crystals, this is a presolar grain from a meteorite, but imagine this crystal in this AGB star basically absorbing light from the central, the very hot central star that's becoming a white dwarf. That light is absorbed by the silicon carbide and then re-emitted at 11 microns. And we can see that and say, oh, there's silicon carbide there. So a nice connection between the astronomy and the laboratory work. But the grains can tell us more. And this is one example of this. I mentioned we use these lasers to measure these heavy elements. In this case, we're talking about strontium and molybdenum and barium. And don't worry about these units, but what we're looking at is the difference in each of these isotope ratios relative to terrestrial or a solar system. And really, really low value basically means you have less of it. So essentially, like all the molybdenum isotopes except molybdenum-96 are depleted. And we already thought that molybdenum-96 is basically only made in AGB stars, whereas these other isotopes are also made in supernovae. And therefore, it's not surprising that this pattern looks like this, but it also gives a very precise measurement of this pattern that goes back into the stellar models to help us better understand how these heavy elements are made by neutron capture. And this is just another example, like I had of the oxide grains, of we can compare specific stellar models to the grains that have different parameters of the models. And the stellar modelers really love this because it helps us better understand how these stars evolve, because there's still a lot of uncertainty in the details of how stars evolve, especially in these complicated later stages like AGB, of how material gets mixed between different shells, how convection works, what the exact temperatures and pressures are, which goes into the nuclear physics. So these grains provide snapshots of actual stars that can be, the models can be tied to. So very, very valuable for testing testing theory with very high precision. And I showed that comparison of oxygen and carbon isotopes to astronomical observations, because those elements can be measured spectroscopically. But We will never have the technology to measure the strontium isotope composition of an AGB star through a telescope. The strontium's just too low in abundance, and the shifts in spectral lines are too small to be discerned. So this is the only way to get at this data. So it's a unique way of studying stars. We also can look at the grain structures, what they're made out of. And what we're looking at here is another one of these aluminum oxide grains. And a postdoc that was working with me and another colleague named Aki Takigawa used an ion beam to cut a thin slice through this micron-sized grain to make a very, very, very thin slice of it and put it in the transmission electron microscope. And so these spots here, if you're not familiar, are an electron diffraction pattern. So it's how electrons are basically diffracting off of the crystal lattice. And it's hard to see, but these big black dots are what you expect to see for a pure aluminum oxide grain. But there's other little spots in here that are related to crystal damage. And you can see that in these images here, that there's crystal damage, and it's also associated with magnesium. The green bits are magnesium. And remember, the magnesium in these grains is coming from aluminum-26 decay. So we're looking at this history of this grain where you had aluminum-26 radioactively decay, release some energy, and disrupt crystal bonds in this little object. So incredible detailed work on this. There's also this little hole in the side, and we think this is an impact crater. This grain was in interstellar space for some period of time, maybe 100 million years. Some even smaller grain hit it and knocked a little crater out of it. These are some similar measurements, but of silicon carbide grains, and what we're looking at are element maps. This is a silicon carbide grain. That's just kind of what it looks like in electrons. But when we look at the chemical map and the scale here, that's 200 nanometers. So the detail we can do this is insane. You can see there's little subgrains of titanium carbide, these green things. But you can also see that there's aluminum, and it's not homogeneous, that this thing has growth rings, where when this grain was crystallizing in a wind of this AGB star, the amount of aluminum was either changing, or the temperature and pressure conditions were changing as this grain condensed to have different amounts of aluminum go into the structure. And then to interpret this, you have to go into detailed thermodynamic modeling and material science knowledge and all this. But it's very, very informative. Again, unique information about stars by studying microscopic bits of dirt in the laboratory. So how much time do I have? Oh, good. I'm going to talk another chronicle that was supposed to be in a Star Wars font. One more story about a grain. I don't remember which one it was, which story I'm telling. Or maybe I have two more stories. We'll see. Anyway, another story. 5 billion years ago, part of another molecular cloud collapsed to form a much more massive star. Our first one was 2 solar masses. This one's 15 solar masses. So it's a B-type star, bright blue, burned hydrogen in its core for only about 10 million years. Massive stars, because they have so much mass, they get much, much hotter. They burn much, much faster. So it takes 10 billion years for the sun to burn all its hydrogen. It takes 10 million years for a 15 solar mass star. When it became exhausted, it became a red supergiant like Betelgeuse, one of the most famous red giants. And then for a while, rapidly burned through heavier fuels. In this case, the helium burned to corrupt carbon, but then that core collapsed and started burning oxygen and carbon to magnesium, to neon and other heavy elements, to silicon, until eventually became nickel-56 in the core. Nickel-56 is the most stable nucleus, which means that beyond that, you cannot make any energy by fusion, because all the reactions you don't have any more exothermic fusion reactions. So at that point, the star loses its battle with gravity. It can no longer make energy in the middle to fight back against gravity. And before that happened, this is kind of an incredibly oversimplified cartoon of what a massive star looks like before it dies. It's got an onion scale structure where as you go in, you get layers that have seen increasing degrees of nuclear burning. So you have a hydrogen envelope, and then a carbon shell, and then an oxygen shell, and then a silicon shell, and then a nickel core. But it can't fight anymore against gravity. The core collapses, bounces back, and ejects most of the material of the star in what we call a type 2 supernova. So this is a before and after of a very, very famous supernova that went off in 1987, called 87A. That's what it looked like about 10, 15 years later. You have these rings of expanding material into space. This is another supernova remnant, Cassiopeia A. This was taken in X-rays by the Chandra X-ray telescope, and you're seeing the red is silicon gas coming out in jets from the middle of the supernova. So these are incredibly energetic, incredibly complicated environments. And by energy, for example, we're talking about the equivalent of 10 to the 42 M&Ms in a supernova explosion. So, relevant to my Stardust chronicle, during the explosion, one of the important isotopes that's made is called titanium-44. And this is happening during the explosion. When the star explodes, you're at such high temperatures and densities that you have all kinds of crazy nuclear reactions going on. And you make something called titanium-44, which has a half-life of only 59 years, and it decays to calcium-44. And when this supernova was exploding, some of that titanium from way inside got mixed out to outer layers, to say where the carbon-rich layer, which also has oxygen 18, I'll mention that, from the nucleosynthesis that happened before the star exploded. So now we imagine this ejecta going out into space. So at some point, when it's in this kind of phase, this phase or this phase, some of the gas is cooling and eventually reaches the stage where the atoms can stick together and condense into dust. And so what happened in this carbon-rich layer of the star is you had, first at high temperatures, you had titanium and carbon forming a little grain of titanium carbide, and a rare mineral. And some of that titanium was titanium-44 from the center of the star. And that titanium carbide, as it cooled, then started collecting carbon atoms, like I showed that image earlier on, and eventually formed this ball of carbon. So it's mostly graphite, but it has this titanium carbide crystal. Okay, same as before. This got ejected from the supernova, spent some time in space, got put into a molecular cloud, our parental molecular cloud. Part of that collapsed to form our protoplanetary disk. Our little graphite grain accreted with other grains to form a planetesimal. That ended up in the asteroid belt. Collisions there knocked a piece of that asteroid into the inner solar system, and it happened to fall into Australia in 1969. And a very large chunk, and it was called the Murchison meteorite. It's one of the most famous meteorites, and this is a kid who had found a whole lot of pieces of this. This is from the Smithsonian. That's just showing a picture of a fireball, not the Murchison one. Australia actually made a postage stamp in honor of this on the 50th anniversary of this of the fall. Anyway, in the 1980s, so now we're going back in time, samples of this Murchison meteorite were dissolved in acids by a group at the University of Chicago. They were trying to find presolar grains. They knew they were there because they were seeing noble gases with anomalous signatures that had to be carried in some really tough substance. So they were dissolving everything else away to find what was holding the noble gases. So it's like burning down a haystack to find a needle. And what they found was that they dissolved everything else. What was left was a little vial full of silicon carbide grains and graphite grains. And they were analyzed at Washington University by SIMS, by my PhD mentor, Ernst Zinner. This technique was just coming alive at that time. And among these grains was this graphite grain. And this measured the titanium isotopes, or the calcium isotopes in it. And we see that the calcium has a bunch of stable isotopes, and we can see that relative to calcium-40, the most abundant, 42 and 43 were the same as solar with errors, but there's 100 times more calcium-44. So just like I said before with aluminum and magnesium, when you see this single isotope effect like that, it's usually the sign of radioactive decay. In this case, this shows that this grain had titanium-44 in it when it formed. Titanium-44 is only made in supernovae, and it only lives for 60 years. So that means that's proof that this grain formed in one of these supernova explosions. The other isotopes are also completely consistent with forming in a supernova. So we also, in addition to having grains from AGB stars, we have grains from supernovae. Astronomers are super interested in supernova dust because we know that there is dust in the earliest galaxies. When we look at galaxies at very, very high redshifts, very far away and very, very, very back in time, we see that they have a lot of dust in them. Even though they're so young, there hasn't been much time for lower mass stars to become AGB stars and produce dust. So it seems supernovae had to make dust, but for many, many years, it was very difficult to detect this dust in supernovae. Starting a decade ago or so, these new telescopes, Herschel and ALMA and stuff, started finding dust in some supernova remnants. So that's an ALMA detection of dust in the center of supernova 1987A. But we have actual grains that we can say come from supernovae, so we can answer some of these important questions about what supernova make, because these dust grains survive in the meteorites. So it's on the order of percents to tens of percents of our total presolar grains are from supernovae. Like I said before, these oxygen-rich ones, these are all from AGB stars. We think all the rest of these over here are from supernovae. It gets very complicated because, remember I talked about this onion shell structure of the supernova. That means there's a huge range of compositions, and we can match the composition of the grains, but it usually means taking a bit from this onion shell level layer, mixing it with this one, and some of this is ad hoc. It seems like the grains tell us that you have to have this mixing, but and I won't explain these in any detail. The point is that they tell us this mixing is occurring, but computer simulations and observations are not yet fully mature enough or at the right scales to really predict the level of mixing we're talking about. There are recent results with 3D supernova modeling that's starting to get much more realistic and closer to the point where we can start directly comparing the models to what we find in the grains. From a nucleosynthesis point of view, we see interesting nucleosynthetic signatures that in some cases were not predicted or not noticed in predictions by supernova models before, but when you go back and look in details at, like, someone's done a computer model to calculate the nucleosynthesis in each layer, and it's like, oh wow, the whatever element this is, molybdenum in a silicon carbide grain has this weird signature of these peaks in these isotopes, and discovered, oh, that's in this shell of a supernova model. No one noticed it before, so it's kind of cool. Other kinds of mixing, a lot of interesting papers that are way beyond the scope of this talk, because I'm almost out of time. So I was going to do one more chronicle, but I think I'm just about out of time, so I'm going to go really quick. Another low mass protostar, 1.5 solar masses, became an AGB star, did the usual thing, but in this case, 3 different crystals formed and stuck together in the outflow of this star: a calcium-rich silicate, an aluminum-rich oxide, and a titanium-rich grain. It was incorporated into a disk, did the usual thing, spent time, ended up on Earth on a meteorite that landed in Australia. This meteorite is called 00526. I was part of the field expedition in Antarctica in 2001 that actually collected this meteorite. And I took this photograph in January of 2001 of this meteorite sitting on the ice. We don't know when it landed. That's a picture of me collecting some meteorite there. And it turns out just a few years ago, I had a postdoc looking at a sample of this meteorite. It's really cool to work on a meteorite you helped find 25 years ago. And this postdoc discovered this really weird composite grain. This is a chemical map made in an electron microscope showing there's titanium-rich material, aluminum-rich material, calcium-rich material, and these are isotope maps showing it's anomalous. And what I want to say is we did follow-up measurements of a whole lot of elements. When you have this kind of aggregate grain of different mineralogies, there's a lot of elements to measure, and that's really, really valuable, because then you have a whole lot of constraints here. This is a whole bunch of different isotope measurements that are for a single grain from a single place. So any model that's going to explain this grain has to explain all of these data. And I think I have a pretty good story for it. It says in prep. It's actually in press. I put the wrong word there. So I have a paper on this trying to go through the detailed explanation. I can't explain every isotope ratio. There's still some puzzles there. But this just is a story to show, I wanted to mention Antarctica, but also to show that we're still finding new and interesting things like these aggregate grains of different minerals. And unfortunately, we tried to do a lift out of this to do transmission electron microscopy, and the instrument failed and we lost it. So that would have been really, really useful too, to try and understand some of the physical chemistry of dust aggregation in stars. So that's all I had to say. The main story here is to convince you that there are tiny dust grains that are from ancient stars, billions and billions of years ago. They survive, and we can find them in primitive solar system materials. They formed an AGB star supernovae, probably some other sources too. We have some we think are novae. Wolf-Rayet stars are a possibility, but we're not sure. And they provide unique constraints into all kinds of interesting processes in space. And I will stop there and say thanks and take any questions.
So for the questions, we'll have our wonderful ushers will come and bring you a microphone. And what are some good sources to reference when asked about 3I Atlas? There are so much crazy information about its composition. Titanium, CO2 abundances?
Okay, so I don't know that much about 3I Atlas, but I do know, I can't say what the best references are. There's already a lot of published scientific papers discussing it. What I would say is the one not to trust is anything by Avi Loeb from Harvard College. He is convinced it's an alien spacecraft, and that's completely inconsistent with all of the data we know about this comet. What we know is there are some unusual aspects to this comet. That's, if you don't know about it, this is a comet that was discovered last year that has been coming through the solar system, but is from it originated outside the solar system. Some of its chemical components that have been observed are unusual for typical comets, but everything that's been seen in it chemically is within the range of what we've seen for normal comets in the solar system. So there's nothing unusual about it that would suggest it's anything but a ball of ice and rock hurtling through space and losing some material because it's heated by its proximity to the sun. So, no.
So, in our brief conversation before the talk, you mentioned that you're thinking about trying to get a NASA mission together to do a sample return from a comet. From a perspective of what would be the most interesting to do in the lab, would you rather the comet or asteroid be a solar system comet or one of the interstellar ones?
Ooh, that is a super interesting question. I would actually pick an interstellar one. We already have samples from, even though from solar system ones. They're not ideally collected. We have particles from comets that hit the atmosphere and are collected by high-flying spacecraft. They're very difficult to study, but we've studied a lot of them, and so we have some idea. And there was a mission called Stardust that flew through the tail of a comet, bringing back dust to Earth, and we were able to study that. There's a lot of sampling biases and problems, but at least we have data about the solar system. And what we learned from Stardust was that the comets have a lot of material from meteorites, that their stuff's gone out. Having an actual sample of a comet from another solar system, especially if, as we hope for our mission, we could sample the ices as well. We want to bring back the sample cold and have measure of the ices. Knowing like the isotopic composition of water ice from a comet from another solar system could be extremely interesting in terms of understanding chemical evolution in the galaxy. Unfortunately, it's not going to be possible because to get a mission selected, you have to know already what comet you're going to go to and show you can get there. And a sample return from an interstellar comet would be a very difficult mission to plan. The European Space Agency is planning a comet interceptor mission, which the idea is to put a spacecraft in space that then sits and waits for an interstellar comet to come so it can go fly to it and study it. It can't do sample return. That's still amazingly cool that they're planning to do this, and I hope they get lucky. That, you know, if they don't get one, they'll just, before they die, will pick a solar system comet to go to. But that's a really good question.
Thank you, Larry. That was wonderful. I have what I think is probably a very naive question, but when we were talking about the type 2 supernova, you said, you know, the end product is nickel 55 or 56. My understanding was that it ends in iron because, so.
I should have been a little clearer. Nickel 56 is radioactive.
Okay.
And so it becomes iron 56.
Okay.
And in fact, it's a lot of the energy you see in a type 2 supernova in the early years is from decay of nickel-56.
So thank you.
Sure.
And the last one, again, is probably silly, but all the samples seems to be collected from Australia. It's just like we know where to look, or is it just a coincidence?
No, I showed one from Australia, one from Africa, and one from
cool.
Antarctica.
Okay.
So the meteorites fall all over the Earth.
Yeah.
So most of them hit the water. It turns out deserts are really, really good places to find them, because if a meteorite falls in Nebraska and you don't see it fall, now everyone would see it fall, but before everyone was interested in meteorites. After 50 years, you wouldn't recognize it as a meteorite because of the water interacting and weathering it.
Mm-hmm.
Whereas you go to a desert, like out much of our state, or Antarctica, which is an incredibly dry desert, or the Sahara, meteorites can last thousands of years without weathering away. And it turns out Antarctica also has glaciology processes that the meteorites fall all over the continent, but they get trapped in ice sheets that then move towards the coast and then get trapped behind mountain ranges. So you have ice fields with lots and lots of meteorites that have been collected all over and then concentrated nicely for us. It's a really nice thing nature did. And that's why we go to Antarctica to find them. Mm-hmm. Meteorites are big business. There's a lot of people who collect them and trade them and buy and sell them. And so they're worth money. And this became knowledge in the last 20 years in Northwest Africa and the various countries where the Sahara is. And there are all kinds of, people who live there who are Bedouins or whatever and wander around in the desert, move around in the desert. And they have learned that, if I see a rock, I should pick that up because some Western guy is going to give me a lot of money for it, which means we now have thousands and thousands of meteorites being found in the Sahara and coming into the community. And there's kind of a parasitic relationship between the meteorite dealer collectors and the scientific community, kind of like there's between fossil collectors and the paleontology. The meteorite dealers need the scientific community to validate this is a real meteorite and tell them if it's an interesting meteorite. And of course, we need them to find them. So there's rules like if it's going to be an officially named meteorite, a chunk of it has to be provided to an official repository, a museum or a university, to be available for scientific research. So any meteorite that's found, if it's going to be officially a meteorite, some of it will be available for science. Long-winded information about meteorites. The meteorite I handed around, which I hope I get back.
I'm keeping this now that I know that.
That's a Northwest Africa meteorite. So that was found in the Sahara. I bought it on eBay, and I bought that particular one because it's more or less the exact type and size of the typical meteorite you find in Antarctica. But I couldn't keep any of the meteorites we found in Antarctica because they all belong to the U.S. government. Mm-hmm. So I bought that one so I had something like it.
Sounds good. Thank you so much.
Sure. And if anyone ever, we have at Arizona State has one of the best meteorite collections in the world. And we have a lovely gallery, and we already set up like a museum thing, but also have a vault just full of thousands and thousands that's incredible. So if you're ever at ASU and want a tour of that, I can arrange for it. I'm married to the director of the Meteorite Center. She won't give me a key to the vault, but she'll show other people the vault.
So we have these dust grains that are isotopically anomalous, and we could tell that they're outside of our solar system, but how do we date them and tell that they are pre-solar? I'm sorry if I missed anything.
The reason we know they're pre-solar is that they formed in other stars, and they were already present when our solar system formed because they're trapped in these rocks that formed very early on. Because there's no way an AGB star introduced dust to the solar system after the solar system formed. So that's how we know they exist. There actually are a couple of studies using some isotopes to try and track how long, to actually calculate the absolute age of these grains based on isotopes affected by galactic cosmic rays hitting them. So if the grain's in interstellar space, galactic cosmic ray may zip through and break up a silicon nucleus and make a neon-21, for example, which is a rare neon isotope. So you look at how much neon is there, you can tell how long the grain was in space. There are a couple papers doing this. The uncertainties are huge, and it's only possible in the biggest grains, which are really unrepresentative. But those results indicate ages of anywhere from 10 million to 500 million years. So these grains are living. Those particular grains are absolutely pre-solar, and back to, could be back to 6 billion years or something. It's a good question. Yes. Oh, need the microphone.
Thank you.
Okay.
I kind of have two questions.
Sure.
The first one, I kind of went over my head. Do HEB stars stand for anything, or is it just a silly acronym?
Oh, you missed it. It's asymptotic giant branch.
Whoa.
And it
Okay.
refers to where they lie on a diagram called a Hertzsprung-Russell diagram, which is
Okay.
used in astronomy.
And then the second one, how can you tell that the meteorites and comets you collect and observe are interstellar or not?
If you just collect something on the Earth, you can't tell. The reason we know there's these comets are interstellar is we can calculate their trajectory. You watch it as it's moving, and you can tell it is not on a bound orbit around the sun. So most comets you look at, you can calculate it until it's on this elliptical orbit around the sun with this period. When you do these interstellar ones, they're on a hyperbolic orbit, and you can just predict that, you can go back in time and see this came from outside and it's going back out. So it's all about orbital dynamics.
Thank you.
Sure.
What kind of analysis and information do you get from ice samples versus like dust samples, or is the information you get relatively similar?
Oh, for a comet?
Yeah.
That's a good question. So basically, what we know about comets is, a lot of what we know about comets is from their volatiles. So when the comet comes close to the sun, the ices evaporate, and we can use spectroscopy to measure all these molecules and try and figure out, make sense of how this comet formed early in the solar system. So it ties more into the chemistry of the protoplanetary disk, the gas chemistry, as opposed to the dust chemistry. So it's complementary. When this protoplanetary disk is evolving, you have things like water and other volatile molecules play a very, very important role, but then don't end up as a big part of the solids. And so the ices should provide more information about that aspect of planetary evolution, whereas the dust tells us about condensation and ages and things like that. It's complementary. That's a lot of questions. Okay, thank you so much for coming.
All right, if you guys are in general astronomy right now and you haven't already checked in, we'll have the sheet outside by the desk. Again, thank you guys so much for coming. Please check out our upcoming speaker events, and let's just get another round of applause for Dr. Nittler here.
Thank you.